Hi everyone, so in this video we will solve again this exercise which I already solved in the live lecture, but for those of you who weren't present I will repeat the solutions and help you how to think of the solutions if you face such an exercise in the exam. So here what we have to do is we have a reaction and we have to figure out the products of the reaction, and sometimes the question in the exam comes as also to specify what type of reaction it is. So how do we proceed in this case? So in the first example, we have a haloalkane, which is this one. So we have, for example, this is an alkane because only single bonds, and this is the halogen. And here it's reacting with a nucleophile. So this is a nucleophile. So the first thing to do is to check if we have double bonds or just single bonds, because you know double bonds are normally also attacked. And I explained this earlier, but I will repeat it a bit here. In this case, we don't have a double bond, but we have this chlorine, which normally is substituted with a nucleophile. But if we don't know this, so we have this nucleophile. First we have to check, do we have a nucleophile, do we have an electrophile, or do we have a radical? So a nucleophile is an element with a negative charge. So this is a nucleophile with a negative charge. And nucleophile means that an element which likes to be friends. Phile is philia. Philia is friendship, and it wants to be friend with a nucleus, and the nucleus is normally contains protons. So the nucleus of an element contains protons and has a positive charge. So something which wants to make friendship with a positive charge is definitely a negative charge. This is a nucleophile, which is the case here. So the OH minus here in this example is a nucleophile. And therefore we might think of a nucleophilic substitution. If we have an electrophile, then it should have a positive charge, an electrophile, because it wants to make a friendship with an electron, right? And the last thing we can get is a radical element, which has some, can have, this, for example, or whatever. The most important is that it has one free electron in its valence shell. And this is a radical. And this is a very reactive element. And normally we have, for example, a Cl2, let's say, or for example, peroxide. So we have two oxygens. H2O2. And both elements are split equally with a source of light. So the bond is broken with equal to free electrons, giving us two radical elements. And this element is normally very reactive because this free electron wants to satisfy its octet rule, and it tends to look for another radical element which has also a free electron to bond with. Or it doesn't have to be a radical, it can be a normal element, and when it bonds with this element it transforms it to a new radical. But in this case we don't have any of the other two, we only have a nucleophile. When an alkane or a haloalkane is in contact with a nucleophile, what happens? Normally we have a nucleophilic substitution when gets in contact with a nucleophile. And this is in this case we can get two different possibilities for the reaction schemes, both leading to the same end product, which is the Cl will be substituted by the hydroxide and we will get an alcohol. So it can happen either way with the SN1 or SN2 reaction, but at the end we get the same product. So what is the difference? Let's recap. So what we have here is we have an alkane first, which has one of its elements some halogen, let's say a Cl. So we have this H3C bonded with a Cl, and this Cl is released from the other molecule, from the rest of the molecule, with an excess of electron. So with the electron of the C, the carbon will release this bond with the Cl by giving it its own electron. And this Cl will now be released as so it now has, normally this is the state of a Cl without any bond, but now it's released with an extra electron. So it is already satisfying its octet rule by itself, but this is not the usual state of a chlorine, so this is a Cl minus. It has one negative charge more than it should. And by this, we get carbenium. So the CH3 now has one deficit of electron, and therefore it will have a positive charge because its protons are more than its electrons. So this is only a transitionary state. It's only temporary because it released one of its electron with a Cl, and therefore it will be reactive. It will not stay like this because this is not stable for a carbon to be a cation. So this carbenium is not stable, and the carbenium will look for a new nucleophile to react with, and in this case the nucleophile is the OH minus. So it has an excessive electron on the O instead of being like that, like a normal OH. It has one electron more, and this is why it's an OH minus. And this extra, let's say this one, this extra electron, so here we have two electrons, one of the electrons of the oxygen will be credited to the carbon, forming this single bond, and therefore the carbon will satisfy its octet rule once again, and we will no longer have this plus, and the hydroxide will no longer have its negative charge again, because now it doesn't have a excess electron around the O anymore. And the final product will be this alcohol, so will be this CH3OH. So any alkane which has the hydroxy group is an alcohol. Of course, we will talk about it in a later video. So what did we have? We started with a halogenated alkane, and we ended up with an alcohol by just replacing the Cl with the OH, and therefore it's a nucleophilic because it was attacked by a nucleophile. Substitution because both elements were substituted without any extra interference of a third product, for example. So the same reaction can happen leading to the same product, but only with a different scheme. And the difference is that first, the nucleophile, because it has this unstable state where the oxygen has 3 lone pairs, which is unusual. So this excess electron will be credited to the C. And by this, the C in the middle will be, instead of forming 4, so this is normally the state of a C. Here it's bonding with a Cl and 3 different H's. So carbon is capable of making 4 single bonds. And when it's attacked with the hydroxide, this O will credit one of its electron and will still have 2 other lone pairs. So in this case, the C is forming 5 single bonds and now has 10 electrons in total, which is unusual for the C, and it will get to this transitionary state and wants to release one of its element with one of its excessive electrons in order to get rid of the 2 extra electrons. So which element does it release? Does it release the hydrogen, one of the hydrogens, or does it release the chlorine? This has to do with the electronegativity, with the polarity of the bond. And normally, the polarity delta E of the CCl bond is about 0.61, and the polarity of CCl bond, CH bond is only 0.3. So therefore, the CCl is more polar, and if you check the electronegativity table, the Cl, the chlorine, is more electronegative than the carbon. So the electron of the carbon will be closer to the Cl than the carbon itself, although it still belongs to the carbon, but it's closer to the Cl due to this, to the bigger energy of the chlorine than the carbon. And as for the CH bond, it's the opposite. So the electron of the hydrogen is closer to the carbon than to the hydrogen. So the hydrogen is somewhere here, which is far from its electron. And its electron is closer to the C. By this, it has a slightly positive charge. And here it's the opposite. This one has a slightly negative charge and this one has a slightly positive charge. Whereas in the CH, it has a slightly negative and the H has a slightly positive. So if it wants to get rid of the hydrogen, it doesn't make sense because the hydrogen is normally released without its electron. So the electron will stay with the C because it's closer to the C than to the H. And the hydrogen will be released as a H plus ion without its electron, which doesn't help the situation here because the carbon will still have 10 electrons. And this is not normal. So this electron here, which is closer to the Cl, when the carbon gets in this unusual state with 5 single bonds, this bond will get weaker and weaker, and there will be repulsive forces, and this electron, once it's very far from the C and becoming closer to the chlorine, at a certain point, the bond will be totally broken, and this element will be totally released as a Cl minus, Y minus, because both electrons were given to the Cl when it was released. So its own electron and the electron coming from the carbon, forming a fourth lone pair, and this is the Cl minus, which is released. So at the end, we will get the CH3OH, just like the first example. So in both reaction schemes, we get an alcohol. So the Cl minus is substituted with the hydroxide. The only difference is what's happening first. So is the Cl released first and then the carbenium is attacked by the hydroxide, or it's the opposite. The hydroxide, having this excess electron, is attacking the alkane, forming this unusual state, and then the bond with the Cl will get weaker and the Cl is released as a Cl minus. In both cases, we have this nucleophilic substitution where the Cl is completely substituted by a hydroxide, giving us an alcohol. The product here will be the same. The difference is here, instead of being attached to a Cl, now we have a hydroxide. And the reaction name is nucleophilic substitution. So this is as simple as this. This is how to think. So we first think, is it nucleophile, electrophile, radical? And once we know, we have to check, what do we have special about this molecule? Does it have a double bond? No. It has this chlorine, then okay, this is also a nucleophile. Then it's most probably that the nucleophiles were just substituted by each other. So we get this at the end, of course, plus Cl minus. Let's do the second one. So here we also have a halogen, the chlorine, but we have an alkene, so we have a double bond. And so there are two options to think. Is the chlorine going to be substituted, or is the double bond going to be attacked and some element will be added to the, will be bonding with the free electrons after the double bond is broken. So in this case, when we have a double bond, you know that it's a pi system. So the pi orbital is usually, as we learned, is a hybridized sp2, and it has this shape. So normally we have the molecule here, so like C something, and the double bond is sort of some electron density here above and beyond. This is the second bond. So this is the sigma bond, and the pi bond, which is the second one, is this above and beyond. Both constitute one single bond of the double bond, so one pi system. And there is no probability to find electrons here in between, in the middle. So the density of electrons are above and below the molecule, and therefore it's high density of negative charges. So normally it's attracted by an electrophile. If you remember, an electrophile, we said that's something that wants to bond with an electron, and therefore it is a positive charge. So like, for example, a proton, H+, could be possibly attacking this double bond because it can be attracted to this electron density somehow. But here, in this case, we have a nucleophile again, just like the hydroxide. So the cyanide is also in an ion, and it has a negative charge. Normally it's a C making triple bond with N. And and this is an anion, so it cannot be attacking the double bond because it will be, on the contrary, repelled by the double bond. So negative and negative, minus and minus. And therefore, we have to consider this again. So we have to consider, since it's a nucleophile, we have to consider once again a nucleophilic substitution. And we have the potential because we have also a nucleophile, which is the chlorine, attached to the molecule. And therefore, it will be substituted like the same reaction scheme that we discussed for the first reaction. The same happens here. We have also a nucleophilic substitution, and the new molecule will be Cl. So you can replace either this Cl or the other. It doesn't make a difference. Then we have this. And here we will have the cyanide plus Cl minus. So these are the products. And it's called, again, nucleophilic substitution, as we said. Let's do the third example. Here, as you see, we have an alkene with this double bond. So, yeah, we have an electron density. We have to see, there is no other thing special about this element except for the double bond. So most likely the reaction will take place in this area. So we have to check if we have an electrophile, because as we said, it's an electron density. So it should be, we should have something with a positive charge reacting to it or attacking this double bond. So we have this HCl, which is an acid, a strong acid. And a strong acid usually has a tendency to release its H+ ion. So once it does that, we have this proton with a positive charge. So this H+ will attack the double bond. And what's special about the H+ ion, the hydrogen only has one electron and one proton, and when it's H+, it means it lost its electron, so it doesn't have any electrons at all. And when it attacks this double bond, it bonds with one of the carbons of this double bond between the two carbons. So let's say this is carbon number 1, this is carbon number 2. So let's say it's bonding with carbon number 1. How does this happen? When the double bond is broken, a double bond is created with two electrons, one electron belonging to the first carbon, one electron belonging to the second carbon. Once it's broken, it's given, both electrons are taken, for example, by the first carbon or the second carbon. Let's say they are both taken by the first carbon, and one of them is granted to the H+, so that it becomes a normal hydrogen and satisfied its octet rule, let's say, but it's not octet, it's 2 electrons. So by this electron number 2 will have a deficit of electron, because this electron, its own electron, was taken by the H+. So this one here will have a positive charge because it's lost its own electron when the double bond was broken. And now when this acid was decomposed with H+ and Cl-, the H+ was bonded with the first carbon. Now the Cl-, Cl has normally 3 lone pairs, and because it's a Cl-, so it takes the electron from the H and becomes a Cl-, so it has a 4th lone pair. So it has 1 electron more, and it's not, it tends to bond with a positive charge, of course. And since this carbon now has a positive charge, it's a carbenium, and it's only a transitionary state, which is not stable for a carbon. It will then credit one of its lone pairs, so the 4th one will become a single bond with the C, with the second C, which has a positive, which has an electron deficit. So this lone pair will become a bond, 1 electron remaining with Cl, and the second electron will be credited again towards the C. And by this acid was fully added to the molecule. 1 carbon has captured the H, and the second carbon has captured the chlorine. So we have here an addition, and it's called an electrophilic addition because the first reaction happens due to the presence of an electrophile in the acid. So yeah, it was an electrophilic addition, and the product will be this, like this. So we no longer have a double bond. Instead, one C has captured the H and the other has captured the Cl. Now the H, as we are not writing all the other H's, you don't have to write it as well, but if you want to write it explicitly to say that it's captured it here, it's fine. But the Cl, we have to write it, so we write it like that. Or if it happened the other way around, the Cl could be here and the H could be captured by the other carbon. Just on a side note, here in this case, so both carbons of the double bond are secondary carbon, because this carbon here is bonded to two carbons, and this carbon here is bonded to two carbons. Therefore, both are secondary, so both have equal chances to capture the Cl. As we discussed in earlier lessons, we said that the highly substituted carbon would normally capture the halogen. And in this case, there is no highly substituted, both are secondary. But if we had, for example, let's say that this does not exist and this is the whole molecule. In this case, we have one carbon here, which is secondary, and one carbon which is primary. So this carbon has the highest probability to capture the Cl because it's more substituted than this carbon, and therefore it's important to write the molecule like this. To write it like this, with the Cl here and not here. Although this is possible, but there's a higher probability that the secondary carbon will capture the Cl. And therefore, just to show that we understand that, it's better or most important in the exam to credit the Cl to the secondary carbon. And the other one will just capture a normal H, which is become CH3 at the end. So, yep, in this case, if this was the case, then it's important to put the Cl on the second carbon. But since all are equal and both are just secondary, then it doesn't matter where to put the chlorine. And we already explained why, because when we have, for example, a primary and a secondary, or for example, a tertiary carbon even, so for example, if a carbon is bonding to 3 different carbon atoms and not just 2, then it will have a higher probability to get the halogen, whatever, if it was chlorine, fluorine, bromine, whatever. So why is the case? Because when the hydrogen attacks, it will attack the least substituted one. So it will attack this one and not this one, for example. It will attack the double bond, but this carbon will bond to the H and not the secondary one, because if it bonds to this H, this one will become positively charged, right? Because this carbon credited both electrons of the double bond to this single bond between this carbon and the H plus, right? Because we said that the H plus does not have any electron for itself in the first place. And therefore, this carbon here will become positively charged. And because it is surrounded by 2 different carbons, and you know each carbon has normally electrons around it and bonding with other bonds, so 8 in total, it has a higher probability to saturate itself from neighboring electrons. So you know the electrons are all over, they are circulating everywhere, they are not just in one place. Sometimes they keep fluctuating, these charges, and sometimes they get close to the C. So just for milliseconds or even less, it tends to get back the electron which it lost, and to stabilize this positive charge somehow. And when it's a secondary carbon, then it has a higher chance because there are more electrons around 2 carbons than around 1. And if it's a tertiary carbon, then it has even more electrons surrounding it to just saturate its positive charge for just a fragment of millisecond, right? But it's still important. So for this reason, it's highly or more probable that the primary carbon will form this bond with the hydrogen, because it does not want to get this positive charge, because it has a very low probability to stabilize its charge. It's only bonding to 1 carbon here, and because it's an end carbon and it's only bonding with 1 carbon, so it has low number of neighboring electrons to stabilize its charge if it becomes positive. And therefore this CH bond is usually stronger than a CH bond with a secondary carbon or even a tertiary carbon. Although they are like the polarity is similar or even equal, but they are a bit different. So that this delta plus delta minus is varies a bit, although it's the same hydrogen and the same carbon. But where it is located has an influence on the polarity. And when it's a primary carbon, the bond between C and H is stronger because the carbon fears to become unstable with a positive charge, because it cannot stabilize its charge with as much neighboring electrons as a secondary or a tertiary carbon would. And this is the main reason why when it's attacked by a nucleophile H+, this H+ will most likely bond to the primary carbon and not to the secondary carbon, if there is such a case. So if the double bond exists between two secondary carbons, that means that both are equal and both will have equal chance to get this, to capture this proton, this H+. But if we are talking about one secondary and one primary, or for example, one primary and one tertiary, then the H+ will bond to the primary, and then the one which will get the positive charge, which will lose its electron because it does not fear to lose its electron, it's okay, because it can still stabilize itself from neighboring electrons, is the secondary or the tertiary carbon. And this is the one that will later on be credited with an electron from Cl- and will capture the Cl. And that's why it's important when we have a primary and a secondary carbon in the molecule to place the Cl on the secondary and not on the primary, for this reason. But otherwise, if both are secondary, it doesn't make a difference. We can place it here or we can place it there. It's okay in both cases. Now let's check the fourth example. Here we have a double bond, which is interesting for us, and we have a Cl2. And Cl2 cannot become an anion, obviously, cannot become a cation. What it can become is a radical. So because it's an equal molecule composed of equal elements, with a UV light, this bond is broken into two equal elements, and we will get this radicalic reaction. This Cl is highly reactive because it has a free electron, as we said, and it tends to also react on the double bond. What happens in this case? This double bond, the second one is broken. So this double bond is broken, leading to two electrons. One of them is making a single bond with the radical chlorine, and the second one is remaining free, giving us a new radical. But this time the radical is a chain and some alkane. So for example, let's say that this one got the Cl, and it becomes a radical molecule. And again, the reaction continues on and on. It's a radicalic chain reaction. And at the end, we either get a similar chain again, which is, let's say, also a radical, and both of them will bond together. So we will have some long polymer with chlorinated alkane, some chlorinated alkane. Or it will continue, the same one will bond with another chlorine, and the reaction will end, for example. If it bonds with a new chlorine here, which is also a radical, then the reaction will end here. Otherwise, there are different possibilities, as we discussed that earlier. So there are three steps in this case. There is the propagation, the initiation phase, which is when the chlorine bond is broken, giving us two radicals. Then there's the propagation phase, when the alkane captures one of the chlorines and becomes a radical itself, and the reaction will continue on and on and on until all the molecules in the reaction are no longer radicals. So all of them are somewhat bonding together. We can have a chlorine radical bonding with another chlorine radical, because we don't just start from one single alkene with one single chlorine. No, we start from thousands of those, or even millions, and the reaction will continue on and on. So the possibilities are a chlorine bonding with a new chlorine, radicals, and we have by this the termination phase when all the radicals are bonding together and we don't have any radicals anymore in the reaction, in the products. Or as I said, we can have two alkanes radicals also bonding together, so we have some chloroalkane chain here, which will be an open chain. And there's also a third option where the double bond will still appear, but we have a part which is an alkane, another part an alkene, and they will also bond together. So you can see this, I explained it in the lecture again. And the most important thing is that the reaction will continue until there is no more radicalic chains. So it can capture, for example, since it captures one Cl and still is radical, stays a radical element, it can still capture another Cl because we have many Cl radicals in the reaction. If it's the case, then we will get one chlorine here, one chlorine there, one chlorine here. Because the reaction will continue on and on. So the most important here, since we have different possibilities, the most important thing is to state that at least we have one chlorine attacking the double bond. And we can write the product like this. If we do this, then we get full points, of course, because in this case we know that it's a radicalic reaction. We have to write radicalic chain reaction. And we know that it's attacking mainly the double bond, because this is where there is a high density of electrons. So this radical is most likely bonding with some electron of the double bonds. So this is what's important here to solve such an exercise, just to find out, are we talking about a nucleophile like in this case? Are we talking about an electrophile like in this case? Or are we talking about a radical like in this case? And this is how we can differentiate if we have an substitution, nucleophilic substitution, or electrophilic addition, or radicalic chain reaction. And always consider when we have an halogenated alkane or a chlorination of alkane, that the highly substituted carbon is most likely to get the halogen, to show that we understand this principle. So this was the solution of the exercise, and in the following videos we will proceed with the other chapters.